Alright, we're going to go ahead and start again with section 2. We want to look at the application again of our intermolecular forces. How can we use this information and where does it actually play out? We're not going to spend very long on this, but I want to make sure that you have heard the information, you're familiar with it, so that once you come to your test, there's no more eye-opening experiences. Now, the first thing that we're going to deal with here is we're going to look at liquids in terms of viscosity. Now, we may have heard this before when talking about, usually people talk about the different types of engine oil that we may be using. The thicker that it is, the more viscous it's said to be. That means it's going to be thicker. The thicker it is, the less resistant it is to flowing, the better it will coat whatever material or whatever surface it is that you're trying to utilize. Taking a look at what you have here, viscosities of a series of hydrocarbons at 20 degrees Celsius. We have just a couple of examples, and you notice that as the compound in the molecule gets larger, we're also having an increase in viscosity, looking all the way down to decane, where we have a 1.42 value for the viscosity. This is going to be due to increased London dispersion forces. Make sure that if you're given a question like this, that you give the exact intermolecular force that you are speaking of, not just say because of the intermolecular forces. Now, this is going to take us into also the intermolecular forces with our liquid phase. One of the other application that we look at is with surface tension. Many times we're used to seeing this when we come to water striders or the liquid, sometimes they call the Jesus lizard, the one that can run on water. And it's utilizing the intermolecular forces, the hydrogen bonding forces between water molecules and between other substances in order to be able to do this. Now, what this basically is going to be is that the surface molecules attract inward. What do I mean? So from water has cohesive forces, or it wants to stick together because of the hydrogen bonding. Because of this, it's going to be much stronger on the top because those molecules are going to pull themselves closer and closer together. This goes back to saying, again, the stronger the intermolecular forces, the greater the surface tension we're going to have, versus if we have another, say a nonpolar solution, it would not have much surface tension at all. Now, because of this is going to lead us into what happens when we change phases in terms of energy. This is a diagram you may have seen before last year, but it also gives you the exact changes between our states, the names of them, and the forms that we're looking at, and also whether it increases or decreases in energy. Endothermic processes throughout this whole thing will be melting, evaporating, or boiling, and sublimation. These are situations where energy would have to be put in order to get them to get to those points, whereas condensation, deposition, and freezing are going to be our examples of our exothermic processes where energy has to be leaving the system. Now, we use this information in terms of looking at what's called a heating curve, or also many times a cooling curve. If you're paying attention, you notice that at different points in our heating curve, we have what are called, well, not what are called, but we have these plateaus. What are these plateaus? These are points where the energy, even though the temperature is continuing to rise and the heat is being added, we notice that we sort of flatten out. This is going to allow us to make sure all of the molecules reach the same energy before they break from the liquid phase into the vapor phase, or from the solid phase to the liquid phase. Now, on a cooling curve, you would expect the similar idea. The temperature is going to fall, and then once it levels out, that's going to be about your melting point or your freezing point in terms of your energy, in terms of your temperature. Now, let me go back. Went a little fast. There we go. Now, in terms of our phase change energy, generally it'll take more energy to vaporize a liquid than melt a solid. Why is this? The overall idea that we're going to look at is how many intermolecular bonds will have to be broken. When it comes to going from a solid to a liquid, we don't have to break all of the bonds. We just break many of them, just a few of them, enough to get into what we then call liquid phase, which allow a little bit of chaos or a little bit of disorder in those molecules. But once we go all the way to a gas phase or to vaporization, now we're basically freeing all of those molecules. When we free those molecules, that means all of them have to be able to go their own separate way. So we have to be able to break all of those intermolecular bonds. And this is what you're seeing by your diagram given here at the bottom of the slide. Given the examples of butane, diethyl ether, water, and mercury. When we turn each of these into their respective vaporization or gas phases, we're noticing that they take a varying amount of energy in order to do that. The first three being very low, even to turn into a liquid, whereas mercury takes a little bit more energy. And then to go all the way to a gas phase, 58 kilojoules per mole for mercury, whereas with butane it would only be 24 kilojoules per mole. Now, when we liquefy gases, what we're going to do is we're going to increase the pressure at some given temperature. Now, this temperature many times will be referred to as the critical temperature. This is the highest temperature at which a substance can remain at a liquid regardless of the pressure applied. The basic relationship that we're going to start to see here is, in terms of our liquid and our gases, is if we have the pressure right and the temperature right, we can continue to have a liquid up to a certain point. The critical pressure is, of course, the pressure needed at that critical temperature. What's going to have the greatest factor on this is, again, the intermolecular forces at those temperatures. Looking at a couple of examples here, you have ammonia, looking at the value given for ammonia, for phosphine right under it, for propane, for hydrogen sulfide, and then look at the value for water. It is far above those that were given to you for the other values. And what is the reason? Because of those hydrogen bonds that are formed between the molecules. That's going to increase that critical temperature and also your critical pressure. So a lot of these things go back to the applications of what we talked about before with our intermolecular forces. Now, some of the molecules on the surface level have enough energy to escape the temperature. To escape the liquid phase. These molecules move into the gas phase, of course. And this is what we talk about what happens at that second plateau. Now, as it increases, we increase the amount of gas particles or the particles in the gas phase. We're going to also increase the pressure. And this is going to give us, one, a dynamic equilibrium, as what's given to you here on the screen. The point is when as many molecules escape as strike the surface, as well as it's going to increase what's called the vapor pressure, or the pressure that's exerted on the liquid and vapor when they are in dynamic equilibrium. Depending on how we adjust the pressure and how the vapor pressure is, that'll also allow us the opportunity to then change the boiling point. If the vapor pressure is very high, we'll end up with a lower boiling point, where if it's lower, of course. Now, those that will escape and have a high vapor pressure at 1 atmosphere or at low pressures, those are said to be volatile. So those are usually going to be our ethers, many times our alcohols. These will boil or actually vaporize very, very easily. Wouldn't have to worry about adding too much energy to them. Many of these will do at room temperature. This is another reason why many times you cannot have these things around a flame. Why? Because if you do have them around a flame, it's a better chance that they will ignite and cause other problems, and we don't want that. There are two main ways that we'll use in order to get a liquid to boil. The first way is to increase the temperature. This is the normal way that we would think about it. The other way is to decrease the pressure. This can be done using a vacuum pump or using the example of a pressure cooker. I don't know if you have, your parents have a pressure cooker that they may use, but it's used to cut the cooking time. Why does it do that? It actually raises the boiling point of water because of the pressure that's in there. If it's raised, then it's also going to have a higher effect on whatever it is that you're cooking, be it a type of meat, vegetables, and so forth, cutting that cooking time many times in half. Example given, for the boiling points that increase molecular weight, with molecular weight, as long as intermolecular forces are similar. And so it gives that methane has a lower boiling point than ethane, which has a lower boiling point than propane. Now, this is going to take us into our phase diagrams. And we looked at and we talked about before what happens as the energy changes and goes up here and there. But we also want to look at what happens to the temperature and the pressure, what happens to it as the temperature and pressure increase. Given to you are a couple of different things that you'll need to pay attention to. One, first, is going to be the triple point. This is the point at which all three phases of matter are at equilibrium. This is the point where you will end up with some solid, some liquid, some gas. You notice that it is fairly low. Depending on the compound that you're using, it may be higher or lower. It will adjust accordingly. The other part is the critical point. And the critical point is that part B right here up at the top. This is going to be the point at which the liquid phase, that's the last point in temperature and pressure where the liquid phase can actually exist. And you notice that it's usually far towards the edge of the phase diagram chart. So it lets you know that it can be actually very high pressure with the temperature and still also have a liquid form. Given these two diagrams, you can see the differences between the two. I have water and for carbon dioxide. Notice the slope of the solid liquid line versus that of equilibrium line, Notice what happens between water and for carbon dioxide. You have a different slope here for water. And this is actually letting you know is that it's actually going to, water expands when it freezes. So because it freezes, it takes up a little bit less space, it takes up more space, whereas carbon dioxide is actually going to decrease inside. It's going to contract a little bit. And you notice that phase goes out a little bit further. This brings us to the end of our section 2. We're going to go ahead and pick this up in class. If you have any questions, please write them down, bring them with you, and we're going to go through some examples to see if we can't make this a little bit clearer. Have a great afternoon, and see you in class.